All right, so we'll keep going here. I put up a pretty large set of slides. We're not going to go through them all today, but we'll kind of pick up where we left off once we return from Thanksgiving break. So we talked a little bit about this already, but when we're doing this linear regression, we can use what we call these dummy variables or indicator variables, which are basically just ones or zero are the only responses we see. So like this was like that student athlete variable. It was a 1 if the person was a student athlete, 0 if not. So a lot of times we do, and do this for have a gender variable in there being 1 or 0. We might have a threshold for age. So if the person's over 60, we put a 1. If they're not, we put a 0. We already have seen this athlete variable. And really it's gonna, I guess we could write it like differently to identify like this is a dummy variable, but usually we just kind of write it as whatever the variable is, right? Like whatever that variable X represents. And so you don't have to, make sure this is stripping down. You don't have to write it as D. You could kind of still write it as, like, let's say X1. Let's say this is like, I don't know. Well, we had the SAT of the individual. And then here, this was athlete. So you can still write the dummy variable, just like you would a typical variable. But we have to remember the interpretation was basically the 1 unit increase now is going from the 0 group to the 1 group. So here, going from being a non-athlete to an athlete would change the predicted Y value, which we were using GPA, I believe, by whatever B2 is. Okay. So I think I have this in the slides, but I'll write it out here because I think it's, since we have this example we worked through last class, it's good to have a nice reference. So you can almost think about if we were just to have these two X, right, or independent variables here on this right-hand side, maybe wanted to know the relationship between GPA and SAT scores. So SAT scores is my X variable. I come up with my predicted GPAs for any value of SAT score once I have these coefficient values. So it's going to look something like this, where it starts at the intercept, and then, right, this slope is B1, right, whatever that sample coefficient we see is. So what this dummy variable does is essentially say, okay, look, that SAT and predict, the relationship that exists between SAT scores and GPA, that's good at coming up with predicted GPAs for non-athletes. But however, for the athletes, we picked up, eventually we found that there was a positive kind of correlation between being an athlete and then GPAs. So essentially, whenever this variable becomes a 1, right, whenever the person is an athlete, my predicted GPA will be exactly what it was before. Let me turn that off. So, where was I? There we go. So now, when the person is an athlete, I'll have the exact same prediction that I did before, but it'll be adding in 1 times whatever that coefficient on the dummy variable is. So for the dummy variable, it's still going to have the slope of B1, but its intercept will be A plus, not B1, B2, whatever that coefficient was on that binary, that dummy variable. Okay. So it's essentially like adding in these these dummy variables is just shifting kind of that relationship. So you can think about it this way. Maybe all the data for non-athletes looked like this. So that was kind of coming up with a line of best fit for the non-athletes. And then by also including this indicator variable for whether or not the student is an athlete, it allows us to have almost like a separate line of best fit to minimize the errors that we're making for the athletes. Right? If I just try to draw a line that best fit both of these groups, it would be in the middle, and I have errors on both sides. And so including this additional indicator dummy variable allows me to almost have like 2 separate lines of best fit, making sure I can really minimize the sum of my squared errors there. Okay. So we've already talked about how we interpret it. It's basically just like the additional effect of belonging to whatever that group is. This slide's really, we don't need to we'll spend a lot of time on it. It's basically the exact same thing we had before. Here, I was just using D to kind of represent the coefficient that was on the dummy variable. But like I said earlier, it could also just be, we just write out that variable like we typically would. Then it's the same thing as before. We're always going to have this assumption that slope is equal to 0, even if that's the slope on, or that, sorry, I shouldn't say that slope, that coefficient is always equal to 0, even if it's that coefficient on that dummy variable. Oops, move the cursor here, right? So even if it's a coefficient on that dummy variable. And then to get my test statistic, well, if we're always using kind of this assumed true value of 0 for the slope coefficient, then it just becomes take my slope coefficient and divide it by the standard error associated with it. So if we look here, I can write this as D, or I can write this more typically like whatever that coefficient is, because I can ignore the assumption because the assumed true value we're said is always going to be 0. Okay. So got the same sort of steps. Now, I'm never going to make you do this in practice, right? What we're going to actually do is look at, oh, did I not have output here? Let me see, what did I? So I didn't have any output on this one. So maybe I have an example down here. Well, we looked at one last class, so let's just open that one up. That'll be easy enough. So we did, where did I put that? Did the GPA data, right? So why is that not showing up? Oh, I'll go to Canvas. So I know it's under here. So let's go to in-class data. We have this GPA admitted variable. So just as kind of a reminder of some things we talked about last week, all right? If I do run this regression, so I'm going to go to data analysis, my regression option, my Y variable, let's just do GPA. And then we hit our X variable. Oh, should have sent me to the top there. It's annoying. Is going to be SAT and being an athlete. So now I select my labels, we get this output. The interpretation is going to become, the effect of being an athlete relative to not being an athlete. It would change predicted GPAs by what, negative 0.05 here. So the way that we interpret the coefficient is always the same. However, just because we see a value here, if the p-value is high enough, we can't actually say that the assumed true value of 0 isn't the true value. So we look at that p-value, it's 0.26. That's not going to be less than any of our conventional alphas, right? It's not less than 0.1, not less than 0.05, not less than 0.01. So all of our conventional levels, we say we fail to reject the null, where the null is that slope is equal to 0, or that there is an effect of being a student athlete on predicted GPAs. So here, at least at, just including these two control variables on the right-hand side, we said that there's really, we can't say with any statistical significance that there is any effect of being an athlete on GPAs, because we fail to reject that assumed true value on that coefficient of 0. So that's what it would look like with kind of one dummy variable. But what's more useful, right, and something we haven't looked at yet, is including multiple dummy variables, right? So maybe we've got like a qualitative variable that has a lot of categories. So this could be something like years of education, right? Maybe it's collected as, you have some college, a college degree, only a high school degree. So we could basically create indicators breaking those all up into different variables. So I create a dummy variable that's either a 1 or a 0, and it's a 1 if the person only has a high school degree, 0 anything else. We then create another indicator variable, a dummy variable, 1 if they have a college degree, 0 if anything else. Then we include another one, 1 if they have, a doctorate, right, or a master's degree, 0 if anything else. So we could create, several indicator variables from one variable, and then we'll include all of them on that right-hand side as additional controls. Now, I can't put a qualitative variable, right? If I just have the data, it read the data in and it just had the words, some college, college degree, high school degree, I can't put that into my regression. I need to turn that qualitative variable into kind of these separate indicator variables. Another good example of this could be, I think the one that I have here. Oh, so I did do schooling, right? So we could kind of make 1 zeros for each one of these different categories. Now the problem is, and what this last bullet point says here, is that you can include those indicator variables now, right? So I would have like 4 indicator variables on the right-hand side there, all 1 0 variables. However, you need to have a comparison group, right? When we only had one dummy variable, well, the comparison group was like built in, right? It was the effect of being an athlete relative to a non-athlete, the effect on wages of being, male versus being female, right? Well, now, right, if I include all of these, what's the comparison group, right? Because if I had, covered every single possible scenario, then there is no comparison, right? Who would get it, who would be the person that has a 0 for all of these is essentially what you want to think of. So I can, include all these indicator variables and just make sure I leave one out, which I think here, so I didn't do it in this example, but notice I said, do you have a high school degree, some college degree, graduate professional degree? The one that I left out here would have been having below a high school degree, right? That would have been the other kind of the 5th category that I left out. And it usually makes sense to leave out either the lowest or highest category, right? Because, then your comparison is the effect of having a high school degree relative to having no high school degree. The effect of having some college compared to not even having a high school degree. The effect of getting a college degree relative to not even having a high school degree. The effect of being a graduate degree relative to not having even a high school degree, right? So there, each comparison is like, would kind of show you the amount of additional income you might expect. If I'm thinking about maybe putting income on that left-hand side, the amount of additional income you could expect from having each one of these, belonging to these different levels of education. So let's go through an example, I think maybe a little bit easier here. So I think I was like interested in this for some reason. I have a sports econ course, but I know I didn't do it for that. I was interested. I heard something in the news, and I was wondering if there was differences in how much revenue is generated across these different like really large conferences. So you've got like, Ball State is in the MAC, Mid-Atlantic. There's the Big Ten Conference, there's the Southeast Conference, SEC, ACC. So there's all these different conferences. And, people kind of talk about it's easier for different programs because some of them generate more money. So I wanted to kind of take a look at it. So basically what we're going to have are regression results that have revenues of these athletic programs. So this is not just football. This covers their entire athletic department. And here's the indicator variables that I created because I also had a variable that just said conference, and it said, athletic, I forget how you see athletic something conference. But anyways, Big 12, Southeast Conference, right? So I had a qualitative variable. I then created a bunch of indicator variables that were just a 1 if the team belonged to the ACC, 0 if not. 1 if the team belonged to the Big 12, 0 if not, et cetera, okay? So the one that I left out was the AAC, which is the American Athletic Conference, right? So every coefficient here, or every beta, so we sometimes will use these betas to represent our coefficients. The coefficient beta 1 would be, here's the expected or predicted increase in revenue if a team belonged to the ACC relative to being in the American Athletic. Oh, hold on. Hey, he's okay. FedEx guys here. So, and then for beta 3, this would be the effect of a team belonging to the SEC relative to the American Athletic Conference, the one we left out. Hey. All right. So, if I were then to run this regression, so all I did here was have revenues as that Y variable and all my different conferences. Now notice here, I kind of cheated because I used a program that wasn't Excel and it dropped the AAC for me. So this is why I'm kind of these zeros and nums here. It just recognized that oh, all of these groups, like there would be no observation that had a 0 for all of them. So it left out one of them, okay? And it left out the AAC. Now, when I do this in Excel, I would actually have to choose which conference I want to let out, right? Which we'll talk about here in just a second. I thought that would be the one, but we can see here, just being a team, a Division I team in the NCAA, your predicted income, your predicted revenue would be about 51 million for your athletic department, right? So that's just being a Division I program, right? That's in the American Athletic Conference, right? Because if I think about this, let's say, so what I've got is, here's my revenues, and I'm trying to predict them for different schools based off of what conference they're in, right? Well, for whatever group I leave out, right, the American Athletic here, every single one of these would be 0. So when I'm trying to come up with predicted revenues here, all of this would be 0. And whatever coefficient estimate I get for intercept, that's just what the predicted revenue would be. So for, which one did I say was the, I already forgot it, athletic, Atlantic something. American Athletic, right? This would be just the predicted income for the American Athletic. And then if I wanted to predict income for like, I don't know, the SEC, well, that's going to be whatever that coefficient is for the intercept, plus, well, now the SEC is a 1, everything else is 0. So that adds in whatever coefficient is on the SEC conference. And then if I wanted it for the Big Ten, it would be Big Ten, it would just be that intercept plus whatever that coefficient estimate was for the Big Ten conference indicator variable, and then so on and so forth. So we can kind of see here, we can almost like tell which conference has the highest predicted revenue. So if you look here, all we're really looking for to figure out, you know, what conference, if I had a team and I was deciding like, you know, what conference am I going to join? I would look at this and say, well, on average, like if I was to, if a school was to join the SEC, that has the highest, you know, predicted increase in the revenues I could expect. And then second to that, it looks like it's the Big Ten, then the Big 12, then ACC, then I could rank them. And then I start to see, well, if I'm in the American Athletic, I could also think about, okay, my expected is 51 million, right? Because I was the group that was left out. So if I was to think, maybe I want to leave the AAC and I want to join one of these other conferences, what that's actually telling me is here, if I was in the American Athletic and I then joined the MAC, right, or being a school in the MAC relative to the American Athletic, that would actually predict my revenues would decrease by 22 million, right? So kind of showing here that all these conferences that have a negative coefficient, those conference athletic departments are earning less than the American Athletic on average, right? And these are all like pretty significant. Looks like maybe the Mountain West, we couldn't say that there's a significant difference between belonging to that conference and the AAC. But everything else here, you know, e to the negative, remember, this is like this is almost 0. So these p-values are all very low, right? I guess the MAC we couldn't say is any different than the AAC at the 99% level, right? Because the p-value is only 0.017. That's not less than 0.01. Same with the Conference USA. But both those p-values are less than 0.05. So with 95% confidence, we could say like we would expect about 20 million less if we join those conferences relative to the American Athletic. And then the independent down here as well, very high p-value. We can't say that that's any different than the American Athletic either. Okay. So the other thing that's kind of interesting to point out here as well is just by including these conference indicators, we've got an R-squared of 0.79. So just from the conference that a school belongs to, we're able to kind of explain about almost 80% of the variation that exists in revenues. So we're already off to a good start here. Now I might want to start to include some additional control variables like, you know, what state does the university belong to? Is it in a large, you know, metro area versus not? There's a bunch of other controls that we could throw in, but just by using the conference, we're explaining 80% of the variation here that exists in revenue, athletic department revenues. Oh, that's not what I wanted to do. Okay, so here, if I was to ask a question, what conference picks the highest athletic revenues? Just the one with the highest coefficient. Okay. All right, where are we on time? I don't want to make this too long. But so we're at, okay, we'll do one more example. Shouldn't take too long. I think it's kind of interesting. So let's say we had indicator variables for different combinations of like race and gender. Right? So maybe I want to do different combinations of, white male, white female, black female, et cetera, right? I would do like every combination of every racial group and then gender. And then I could kind of run this regression on income. And then all my coefficients, if I leave one of these groups out, that would be the effect of belonging to that combination of race, gender relative to the one that I left out. So what might make sense is if I've got like income, I could, let me see, I didn't have an example here, but on the slide. So let's say I do something like this. Maybe I want to identify, are there any wage disparities in terms of race and gender, right? So I'm going to try to predict income, and I'm going to have all these different combinations. So maybe I'll just keep it easy actually in this one. So for race, instead of doing every single racial category, let's just do kind of white female. Okay. We'll also have kind of non-white female. And then we'll have our third, which is non-white. Okay. Now we could break up, gender and race into more categories here. I'm just kind of simplifying it to make this an easier one. So the group I left out here is white males. So now, whenever I come up with these coefficient estimates, the interpretation is, here's the predicted change in income for a non-white male relative to a white male. So I would imagine if we run this regression, we probably find that all of these coefficients are all less than 0, right? If we just look at the averages, we know that plays out. And I'm guessing most data sets, if we do this and we don't account for other things, right? We started to account for things like the socioeconomic class of the individual, their education level, right? If we started controlling for a lot of these other things, we probably get very different estimates. Like, they won't be as biased, right? But at least here, this would kind of be like a starting off point that if there is any discrimination going on in terms of pay, we would be able to pick it up in a regression like this. Okay. Now, I didn't do that one, but I have one I think is a little more interesting, and it starts to look at, can we identify any type of discrimination, right? So I had this huge traffic stop data, right? And it had officer and driver race. And I thought, oh, this would be kind of interesting, right? So I was kind of thinking, I wonder if there's any kind of discrimination going on, not just like, cross races. So regardless of what, not just, towards Black individuals or white individuals, but like basically if the officer's race is different from the driver, are we seeing they're like issuing tickets at higher rates or arresting at higher rates? So basically what I did was I had all these, I created these 3 different indicators, right? Which was the officer white, was the driver white, or was the officer non-white, was the driver non-white? So kind of like this example I thought about with identifying, was there any differences in wage discrimination, right? Here I'm thinking, is there any discrimination going on kind of from drivers and officers of different races? So the group I left out is when the driver and officer are both white. That seemed like a good kind of comparison group. And then hopefully I don't see, right, any positive coefficients here. Because let's think about this one. So if the officer's non-white and the driver's non-white, right, if beta 4 is positive, that means relative to when the officer and driver are both white, it's more likely that the person who's non-white, right, is getting a ticket. And then kind of here, if the officer is white and the driver is non-white, relative to when they're both white, if this is positive, that tells me that the white officer is more likely to write a ticket to the non-white driver. So that's a bad thing. So hopefully we don't find that. We're also getting control for some things in X. I think I had like age and the years of service of the officer. So yeah, so I ran this regression, right? Looks like it kind of came from Excel here. So I've got all my coefficients. I've got my p-values, which here, everything's significant, right? All these p-values are basically 0. But I see that they're significant and they're positive. So what this is telling me is, relative to when the officer and driver are both white, if the officer and driver are non-white, we're seeing tickets written at an 18%, right? It's increasing the probability that I get a ticket, right? So this is another good thing to point out. So up to this point, I haven't used a 1-0 for a y variable, but I could, right? So here, the regression that was run was, did they get a ticket and all these other things. So when my y, or my dependent variable, is kind of just a 0 or a 1, all my coefficients now start to have the interpretation of, okay, let's say we had age. If age goes up by 1 year, then we would expect the y variable to change by beta 1. But now the y variable, like its units, is essentially probability, right? So going from 0 to 1. So a 1 year increase in age would predict that the person who got pulled over gets a ticket would if the person who's get pulled over is 1 year older, the change in the probability they get a ticket would be whatever beta 1 is, or B1 here. So I can think about here, if the person's 1 year older, there's about a 0.003 decrease in the probability they get a ticket. So the older you get, the less likely it is you get a ticket if you're pulled over. That makes sense, right? You know how to deal with cops a little bit better. Maybe the reasons you're getting pulled over are probably different at older ages. Officers' years of service, same kind of thing. The interpretation would be, an officer who has 1 more year of service, the probability they write a ticket if they pull someone over is about an increase of 0.003-ish, right? Which kind of makes sense. If they're on the job more, they're probably only pulling people over that they know should get a ticket, right? So the more experience they have, like they know kind of, I shouldn't, waste my time pulling this person over if I'm not even going to give them a ticket, or, I just don't know what to look for maybe in terms of suspicious things. I don't know. I'm just kind of telling stories here a little bit with these, but it's stories based off of the data. And then here's what's interesting is, if the officer's white and the driver's non-white, relative to when they're both white, the probability that the person gets a ticket is almost 7% higher, or an increase in the probability of 0.07 it almost. So that is some evidence that there's discrimination going on, right? These white officers are writing kind of tickets a little bit, at higher rates for their non-white, when they pull someone over who's non-white, relative to a white driver. Now, and also holding constant the driver's age and years of service. Now, it'd be better, and there's some of the data I do have. I think I gave it, one of you is using it for your individual assignment. There is the code of the reason for the stop. I didn't dive into that too much, but a lot of this discrimination kind of goes away if you can start controlling for the reason for the stop and things like that. I think this was only when I pulled this data out, I dropped everything other than just the traffic stops. So for speeding or broken taillights. So none of the, got rid of all the, warrant, if they pulled over because there was a warrant out for the arrest or anything like that. So, it's kind of sad. It's evidence that there's some discrimination going on. It also looks like, if I look at kind of when the officer is non-white, relative to when doesn't really matter. So if the officer is non-white, it looks like they're simply always writing tickets at a higher rate than when the officer and driver are both white. And also notice that when the officer and driver are non-white, compared to when the officer is non-white but the driver is white, it looks like the non-white officers aren't really writing tickets at very much different rates, regardless of who the person pulled over is. So it really looks like the discrimination going on is really coming from kind of white officers to non-white drivers, right? But that the non-white officers, they're not really, there's no discrimination. They just give everybody more tickets, right? And I don't know what this has to do. I'm guessing it has to do something with this data set was in this big city in Texas. I think it was Houston. They didn't disclose that for sure, but it's probably that, the different areas in which maybe white and non-white officers are working, maybe they have differences in crime rates. So it's not just the officer being non-white is causing this. It's likely correlated with something else that's important that we left out of the regression. So this is a somewhat simplified regression, right? We don't have a ton of controls, and so we have to be very careful even reading too much into this discrimination because we haven't controlled for a lot of other things. Like I said, what was the neighborhood like that the traffic stop occurred at? What was the socioeconomic status of that county, the unemployment rate, like all these things. But so I showed you some bad news. I guess what's a little bit more interesting, or so we can say some good news, is that if I did the same thing, but I was a 1-0 variable as my y variable. So instead of did you get a ticket, I had a 1-0 variable for did the person get arrested, and ran the exact same regression, so exact same control variables. Well, now it looks like, we'll look here. Well, these are the only two that are significant now. So this is kind of interesting. The older you get, if you're pulled over, it's less likely you end up getting arrested from that pullover, which makes sense to me. And then officers' years of service, as they get older, they're less likely to turn a traffic stop into an arrest, right? Every year they are on the job, it decreases the probability they arrest someone from just a normal traffic stop by about 0.004. So maybe this is evidence that, there's less overreaction the longer and the more experience they have. Or if you're a cynic, maybe they don't care, I guess. I don't know. Now, we're explaining very little of the variation whether or not you get arrested, right? Just about 0.002. So we really are missing a lot of important variables here. So same thing here. I think we're only explaining 0.03, right? So we should take these results with a grain of salt. But I thought it was kind of interesting and a good way to show you how if we did have additional more control variables, we could, the results would be a little more useful. But this would be the same process of how you identify discrimination. So notice here, relative to when the officer and driver were both white, when the officer's white and the driver's non-white, there's a slightly higher probability that it turns into an arrest. However, we can't say it's statistically any different from 0. So that's good. Doesn't look like there's as much discrimination going on, at least in a more intense way, right? So we had that, unfortunately, it looks like non-white drivers are getting tickets at higher rates. However, it's not like those results are turning into arrests, like those traffic stops. And then if we look at when the officer and drivers are kind of both non-white, or when the officer's non-white and the driver's white, looks like there's a slight decrease in the probability that it turns into an arrest. However, those p-values are pretty high. This one's starting to get closer to being significant, but still we can't say that any of these are significant at the 80% level. So bad news. Looks like there's some discrimination going on in terms of issuing tickets based off of race of the officer and driver, but at least nothing significant. We can't say that there's any differences across those groups in terms of that traffic stop becoming an arrest, right? Because they're all, p-values are all less than, or sorry, all not less than 0.1. So I kind of have the summary of these over here if we're kind of going back through and wanting to look at those results. But really, other than that, that kind of does it for me today. We will switch over to looking at differences in slope, just some additional regression topics once we come back on Monday. Okay.